All right. Hi, I'm Rob Clark from the Chrome OS team working on freedreno and uh, its compiler IR3. And I'm here to talk today about the two most exciting things in the world, instruction encoding and XML.
Whoa.
So, um,
Could you hold the mic a little closer?
yeah, I'll try. Yeah. So this talk is about isaspec, which is a thing that we came up with to formally describe the instruction set encoding for what we call IR3, which is basically the instruction set of Adreno 300 on up. And the motivation was to replace what we had previously, which was separate hand-coded assembler and disassembler with various obscure independent sets of bugs and so on, with something that was a little more formal, yet at the same time flexible enough to maintain existing ASM syntax and deal with various weird cases like repurposed bits. Like if these two bits over here are 0, then these two other bits over here mean something completely different, and so on. And also avoid a lot of duplication for instructions that have similar encoding. So the basic design at the top level, the important part is the so-called bitset, which is basically a variable fixed length range of bits that means something. So that's used at the top level to define instructions. It can also be used to define fields that are used by those instructions and so on. And then also enum, which is fairly self-explanatory, and expressions, which allow us to conditionalize various parts of the instruction encoding. So as I mentioned, bit sets are arbitrary but fixed length. We have an inheritance system, so you can define as much as you can in a sort of parent class and then extend that and so on. And then leaf nodes of that inheritance tree form the set of patterns that it tries to match against. So a bit set contains a few sub-elements. Display, which essentially is a sort of template string for how the disassembled instruction looks. Field, which is kind of self-explanatory. You know, these 3 bits here mean this. We have a thing called a derived field, which allows us to deal with situations like, you know, you have the low bits for some field over here, and then they later squeezed in high bits somewhere else in the instruction. So a derived field can essentially combine those into what it actually means. The pattern bits or bits are what get matched against the raw undecoded instruction. Basically, it kind of masks the non-pattern bits out and compares to see if an instruction matches. There's override, which gives you a way of dealing with variations of instruction encoding and also mnemonics and so forth. Gen to let you restrict certain encodings to a subset of generations, because things change over time, and sometimes you end up with something where some pattern of bits means 2 completely different things depending on what generation you're looking at. And then finally, the encode, which maps the IR back to the description. So a simple example here at the bottom is just defining the min f instruction. All of the fields in it come from a parent class, and these pattern bits here are essentially the opcode. So as I mentioned, the display is basically a template string. These like bracketed things get replaced with the value of the correspondingly named field. and then with one special case where name gets replaced with the name of the bit set. So like if that's the instruction name, for example. Field is fairly self-explanatory. It has either a position for a 1-bit field or high and low. Name, a type. The type can be int or uint or assigned or unsigned offset, which gets displayed if non-zero as a plus or minus some field. It can be another bit set itself in the second example here. And the other thing is when you have bit set sources, you can essentially parameterize those. Like think of it as passing a field in that's used by that bit set. For example, a lot of cases, there's 1 bit in the instruction that's controlling whether all 2 or 3 sources are half precision or full precision registers. And then, as I said earlier, you have the derived fields, which uses a similar sort of template string, which just basically just turns into a C expression. So in this case, the field name W is calculated as repeat plus 1 times 32. And then finally we come to the slide full of XML. The override was probably easier to explain by just showing an example. Essentially, it references okay, a little bit of background here. The ALU instructions in IR3 have a repeat field that allow them to access as a quasi-vector instruction. It basically gets repeated, 1 to 3 times. There's separate bits per source instruction, which say whether the source instruction stays, or source register stays constant or increments to the next successive scalar register each cycle. And then at some point, some clever engineer figured out that if the repeat field is 0, we can actually repurpose those bits to mean something completely different. So this cat2, cat3 no encoding expression basically evaluates to if repeat equals 0 and any of the source R fields are non-zero. In that case, it uses a completely different way to display the instruction, because now those repeat bits, or the per source repeat bits, are used to calculate a number of no ops to execute following the instruction, basically to pad pipeline bubbles. So that all explained what this means is within this override, this is a display string and interpret this field as such shown in the top. And then everything outside the override is basically the else case. Yeah, you can think of it that way. And then finally, the encode field. I wanted to try and avoid hard coding the XML to a particular IR. So I wanted to be able to take whatever arbitrary IR and in the encode direction go back to the encoded instruction. So with the inheritance, okay, so here we have sorry, I guess you can't see my mouse cursor. I need a pointer. At the top, you can see the instruction. That's a base class of all instructions. The encode has a attribute called type, which is basically the input to the encode. In this case, it's a struct IR3 instruction. And the case prefix basically is used to calculate switch statement case labels from the instruction name. Because of the inheritance is basically just handled in the Python that parses the XML by merging all of the levels of the inheritance tree. The same goes for the encode, so we don't have to respecify on a leaf node that the encode type is a IR3 instruction. But within the encode, it has this map blocks, which can call helper functions or can just dereference fields in the IR as needed. And then, yeah, finally, to do on our side, one of these days I'll get around to converting the Adreno 200 IR. It's kind of a straightforward-ish fixed 96-bit encoding. We have assembler and disassembler for the firmware that we the Adreno 5 microcode firmware. At some point, I'd like to convert that over as well. Although with that, we have the extra constraint of actually wanting to get an IR, not just disassembled text, out of the disassemble path, because for various reasons, we actually execute the bootstrap code of the firmware in order to like properly locate the jump tables and things like that. Yeah, and you know, possibly it's useful for other drivers. I think I've heard some examples that are enough different that it might not make sense. I mean, there's some variety in GPU shader instruction sets, let's say. But I know there's a work in progress branch out there with etnaviv conversion, and maybe there's some other corners where this is also useful. Yeah, I think that's it. So questions?
Mostly just a comment, and that is that in the bits of stuff that I've been doing with isaspec BK, not having the disassembler, not having the disassembled data structures was kind of a decreased the usefulness ratio, because the one place we are using it right now is in for building the enemy instructions, which is the command stream macro language. And a big part of what we were doing that was building a simulator for it. And I could only use isaspec for it. The other thing that would have been nice is if there was a better way to just dump out a header file with all the enums from the isaspec instead of having those duplicated, because you don't want to include the lots of stuff. And it would have been nice if those would have dump out just the enums so that we could put those in data structures and include them places.
Okay, I don't know if I have to repeat all that or did the catch that on the feed. So the going back to IR and the disassembly direction is a thing that I also need for our firmware. One of the things I was thinking about is just feeding the disassembled text back into the lexer and parser, which is kind of cobbled together, but it could work and it's low effort if you already have a lexer and parser. So yeah, otherwise, you know, I guess we could define something that is the inverse of encode. As far as the enums and the header, that seems like the pretty trivially easy part. The way I've used it, though, in not all cases, enums are, you know, valid C expressions. Sometimes they're just how you want the disassembly to look, which may or may not be the case for you. But I mean, we already have smangling to deal with things that are not valid C instructions, so, or identifiers.
So I looked into using this for the AGX instruction set. The only real showstopper I see from my end is that AGX is variable length instructions, and I did start typing out a branch with like the isaspec and trying to, encode it as a fixed length instruction of the maximum length, and then try to hack around it in the disassembler and the assembler directly. But it ended up getting very unwieldy and kind of losing utility. And so I'm trying to understand how ingrained is that into this? Is trying to generalize isaspec or while using time for that, or is going off and I guess my own thing like usual the right call here?
Okay, to paraphrase and repeat that is, how hard would it be to deal with variable length instructions? And why didn't I? Well, the second part is easy. Basically, I didn't need to. So I think if you can, I mean, how easy is it to identify before you call the decode this thing that it's X number of bits instead of Y number of bits?
You would, and then, I don't want to duplicate all of that information. It's already in the XML, so I guess you could have some complicated multi-stage, dump out the enum, use, like Jason mentioned, use the enum pattern out in the output.
So, I mean,
all of this we made work, but it doesn't know what doing something only for
yeah, no, I think it's probably worth trying. I mean, in the decode direction, maybe an easy option is have different bit sets for each length and have the decode entry point return an error if it didn't match. So you could first try and decode them as the largest size, and if that failed, the next smaller size, and so on. That sounds roughly like that might work. And then I guess in the encode direction, it's something similar. I mean, you could probably do this as kind of like quasi-variable length by just treating all of the, like say I don't know what the actual size is, say they're like 16-bit and 32-bit. So in the 16-bit encoding, just declare all the, remaining 16 bits as don't care. And then the only complexity is the, as you're iterating over, you have a bunch of block of bytes, which are raw instructions. You need to advance the pointer in that some amount, depending on which size bit set pattern it matches. But yeah, that seems like that could work without even really changing much. Yep. All right. It didn't put anyone to sleep yet? Oh, okay. Cool.